Hello, Jordan. Hello, Jordan.
Hey,
How are you?
how are you, Leah? I'm good.
Good.
Getting a little worn down, but hanging in there.
Okay.
Yeah, normally around this time, there's a spring break coming soon that you have to look forward to. And I guess we don't have it this semester, so it's going to be a little unfortunate.
Yes, but my kids have spring break.
Yeah, I think they just do it because I think they're afraid that a lot of students would leave and then come back, which I get. But that break is usually pretty nice because I guess at least for me, sometimes the way my schedule's oriented, every week I have this feeling of like, if I just make it through this week, next week should be easier. And then next week comes and it's still hard.
Yes.
So that's just maybe the feeling I get sometimes.
I could use a
So
spring
that's
break.
why spring break is so nice because it gives you a chance to just, even if you just take a couple days to yourself and the things that you normally do, you just don't do at all. It's kind of refreshing because it gets a little monotonous doing what everybody else wants you to do.
Mhm.
It's hard to keep up. And my research stuff is picked up, and I'm doing more research and just learning about what I'm going to be doing and the processes, and so I've just kind of added that to the plate. So I'm feeling a little worn down. My dad was like, "You're working awfully slow these days at work." And I was like, "Yeah, I'm getting a little behind at work, getting a little behind in school." So yeah, spring break would be huge, but we don't have it. Luke, I saw you're giving a presentation, an
Yeah,
APS presentation.
yeah.
What are you presenting on?
I did some research during my undergrad. So yeah, just sort of presenting those results.
What was the research?
It's quantum computing research. So um, so have you heard of the traveling salesman problem? It's like a computer sciencey
Yeah,
thing.
yeah, I
Yeah.
have
So
actually.
like a professor had an idea for a way to construct an algorithm um, to like search through like permutations of objects. And so, um, yeah, I met with him and I was like, oh, maybe we could try this on the traveling salesman problem. And
Hmm.
so we got some good results for like the most basic um, like case of the problem. So um, that is, yeah, so that's what I'm presenting on is like it worked
Cool.
really well for like a problem you can do in your head, but we're not sure how it scales. So
Okay. I thought that's the situation, but then Bob encouraged me that no, it is straightforward. And so since I have a new hard drive on my machine, so I have to do this anyway. So
What was weird is I installed it on my laptop, and they had like it was almost like a 3-page PowerPoint that took you step by step to doing the Linux stuff. And it worked perfectly. before they had a set of instructions that did not work so perfectly.
Okay.
And so I thought, great, so when I went to install it on my home machine, I couldn't find that same PowerPoint.
Doesn't help, huh? So yeah, but most of you are probably using Windows, I think, and those are using Linux know this in other circumstances, so they're more patient, I suppose.
There's a very good chance you all have to use Linux for certain things because of when you get into research.
True.
I had to use Linux for in my undergrad for computational physics. Yeah, it took me like the first month of the class to figure out how to partition my hard drive and download Linux to my computer.
Okay, that's 3 of you sitting in a line. Okay, so all of us here. Oh, Luke doesn't have a video. It's okay. Yeah.
Yeah, sorry, I'm finishing my lunch and I don't want to be a distraction, so
Well,
turn on it a little bit.
yeah, okay. So let's see. This is homework 6. Student. And there's a homework 7 also, and I'll be going relatively fast in that, I suppose. And this is not due. I don't give any due date, but I'll encourage you guys to go over the thing. If you have taken classical mechanics with me, it's probably the same homework. Or there, I think there I make it due. I don't remember what I did. Okay, and well, that might be a breathing space for you guys. Midterm 2 is on March 30th, which is a Tuesday. And I've been saying that this will be in class and no Zoom. So I think it affects only theory, I suppose. Okay. So we sort of motivated the idea that light actually, or propagation of light is identical for 2 different observers which are moving with respect to each other. And what is the consequence of that? So if you take Maxwell's equation as it sits, and you say that speed of light is a constant, and which would mean that 2 observers see propagation of light, and they all both say that, oh, this is going with speed of light. So what does that mean? So broadly, this will be clear. Trying to more motivate Lorentz transformation. A certain extent derivation, but I wouldn't call it complete derivation, because at the end there will be one place where you will have to actually use connect it with the physics. But there is an independent derivation which I do in classical mechanics, which is more promising in a sense, and it really brings principle of relativity as the centerpiece, and there it is much more a nicer derivation. Okay, here what we are saying is that there is a source, right? So there is a source of light, if you want, and here there is an observer, and that's a distance, and this is light going from here to there if you want. And let's say this is observed by two different people. One is this person. He or she has to measure this distance and how much time does it take. So there is one observer here, and let's say this person is at rest. So again, what he or she does is that measures this distance. Let's call it distance r. That's r. Okay, so this here, I'll try to avoid using r a lot, but so that's my r and that's my gamma. Okay, both are the same. But hopefully, contextually, I'll not be using r very much. So there's a confusion. It's a good case to say that it is gamma. Okay. So that's distance r, and it happens in a certain amount of time. So from here to here, there's two events that happens, and it that is a distance between the two events, and there is a time elapsed between the two events. So I can call that delta r and delta t to signify that this is a difference in position and different time, but I just say it is r and t. There is another person. Let's show it as a car, which is moving with respect to the first person with velocity v. So, and let's say it is going in the horizontal direction. But in general, it's a vector v, but we are going to say it is going in the x direction. So it's, it gets way more difficult when velocity is not in the linearly x direction if it is going in any other direction other than x, y, or z along one of the axes. Okay, that's it. Again, this person measures the distance, and let's say this is r prime, and so he or she measures r prime and t prime. Here it is r and t. Actually, forget r altogether, right? X, y, and z. And there is x prime, y prime, z prime. Then I don't have to worry about r and gammas. Okay. Again, this is the vector from this point to that point. Those are the three components of that. And these are the three components of the vector starting from here to there. So that's a difference between the two positions, and there is a time also. But according to or the understanding we gather from Maxwell's equation is that if this was light that was propagating, then these distances are connected, and it is that remember the light going would be distance is, let me write r is equal to c times t. Right? That's one measurement. And if I write this as a squared quantity, so that's r squared is equal to c squared t squared, which means that x squared plus y squared plus z squared minus c squared t squared is equal to 0. That's your statement that light goes like travels this distance in this much time, and since it's going with speed of light, which is a constant, it's just speed is equal to distance over time. Same thing measured in here. That's equal to r prime square. R prime is equal to c t prime, and this observer will say that r prime square is equal to c square t prime square, and he or she would say this is x prime square plus y prime square plus z prime square minus c square t prime square is equal to 0. And the question one can ask is, what is the connection between x prime, y prime, z prime, and t prime in terms of x, y, z? Is there a connection between them? And learning from Galilean relativity, you say that, okay, let's actually at least make it linear. So assume, assume linear transformation. So you're going to assume linear transformation between them. Now these, you can again say, see, these are the places where you say this is not really derivation, because these are motivated from physics. Why linear transformations? Because if one is going in the forward direction and whether the other is going in the backward direction, that should be the inverse of each other. So those kind of connections allow or require you to actually make it linear transformation. But let's at this stage just assume that. And what that means is that x prime is equal to something, and let's say this is let's say the z direction. So x and y is perpendicular to that, and this is also the z prime direction. So what we are going to say is that let's x prime be equal to x prime be equal to x, y prime be equal to y. That's sort of in the trivial manner. Things don't change. Again, a lot of richness in there. One should argue those things out. But let's keep all the non-trivial features in z prime and t, and let's say this is a, which is a function of velocity. So any function of velocity, and let's say this is z plus b as a function of velocity, which is a function of c times t. So if you want, this makes it easier to see. There's a linear transformation, a times z and b times c times t. But a and b are functions of velocity, if you want. And c, I write c times t because then it's a dimension. Dimensions match with c and z prime. That's the reason why I put c in there. Similarly, c times t prime is equal to, let's say, e, which is function of velocity, times z, plus f, which is a function of velocity, times c times t. Okay. If this was a Galilean transformation, right, if just to, oops, I think I'm not in the, okay. If this was Galilean transformation, what would you say? You would say that a is equal to 1. So this is Galilean transformation. And that's the nice part that I was if you're referring to that article. It doesn't highlight it very well, but one of the derivation involves that you can say in this way of doing, you wonder there are how many relativities possible. Like you have Galilean relativity, you have special relativity of Einstein. Is there anything else possible? And one can show that this is the only two possibilities. There's the speed of light, and there is you say that it is infinite. This is relevant because so this is a just slight distraction. Now you say that information travels at the speed of light, and light is something that is carrying information between two charges. Right? Photons are closely related with electrons. Like if an electron has to talk to another electron or another charged particle, they need to have photons. That's our understanding as of today, that if I'm a charge, you're another charge, I pass a photon and you receive the photon, and that's how you know that I exist. But now if there are two masses, right, they also talk to each other, and there it is not photons, and there it is gravitons. Right? And these days we have detected the gravitational waves, and we know that they exist. And we have not detected gravitons as such, but we know that gravitational waves exist. Is a clear signature that the particle format of that would be graviton. Now we ask the question: what is the speed of gravitational waves? At what speed do they go, by the way? It turns out to be the speed of light again. And there, these are two fundamentally different concepts. One could ask, is it possible, at least theoretically, that they are going at two different speeds? Like photons travel with speed of light c1, or speed c1, which is a constant. gravitons go with another speed c2, which is constant. And that's where the principle of relativity comes in. According to principle of relativity, you can have a fixed speed of light, but you can only have one. You cannot have another one which is a constant. You can have only one. So if you chose photons to be that, then the other one also has to go exactly with that speed of light. If it is something else, it cannot be constant, then it will be relative. Like remember, speed of light is not relative, whichever frame you are, it is c. Any other speed has to respect this relativity, where if you move with respect to it, it will change. It has a complicated expression, point correct addition formula, but it has to. So that's a kind of a neat thing that comes out. And again, I think Rob was asking, should I go over that? I won't go over the derivation here, but I'll give you guys a link. Right? Or yeah, quiz, right? Look up that link in my classical mechanics lecture. So quiz is and 2020. Now that we have, I think we have gone through 1 year. That's what it means. I think we are not at 1 year, right, in the pandemic. Sort of 10-15 days from there. So in 2020 classical mechanics lecture, like there is a playlist to that, like we have here, and it should say Lorentz transformation there. So there I go through a different derivation than this, and there it comes out that there are only two possibilities. Either you have Galilean relativity where c is infinity, or you have one speed of light which is a constant. You cannot have more than. It's a kind of nice conclusion there. Okay, so go through that and get that concept. So that's it. Okay. So why did I do that? Yeah, I was saying Galilean relativity involves A is equal to 1, B is velocity, right? Yeah, B is equal to, no, not velocity, it is V over C, right? Because C has to balance out, because Galilean relativity does not have any information of C. Since I have C in this equation, so it has to cancel out. Right? So it is not that there is information about C, C cancels out. And what is E in Galilean relativity? E in Galilean relativity? And what is F?
V prime over C.
V prime? Did you say V prime? Why V prime? What is V prime? That's all one relative.
Okay.
I think you guys are confusing. I said this is wrong. So in Galilean relativity, what is E and what is F?
Is E C over V?
C over V. Okay.
And F is 1.
This one. That's correct. Try this again. F is 1.
0.
0, yes, very good, right? Because time does not depend on position and relativity, right? Time is absolute. P prime is t. Like Galilean relativity says that z prime is equal to z plus or minus vt, right? And t prime is equal to t. They don't even talk about it. I don't think they say, I haven't read Galileo's work, but I don't think, or I'm not even sure they write it as a principle of relativity, but I'm not sure. It's just that it was very convenient to have absolute time there. It's very much like now, right? this is again a digression, but I think worth asking, why is causality so important? Like today, it's almost an accepted thing in all over around us that you cannot shoot someone and the other person dies before you shoot, right? You do something, cause and effect. You do something and something happens, right? I'm taking the dramatic picture of killing someone. So, but yeah, I'm hopefully, if you allow me, so that is, so you do something and something happens. The present cannot affect the past, but why not? Right? It is mostly because we don't have any great thoughts on it. Like it is very easy and convenient to the other way, and it's very non-trivial to think of a situation where the future affects us. Like movies try to show this to a certain extent, but it gets pretty complicated very quickly. Like even simple concepts get complicated. And that's, I say that because that's very similar to, imagine in 1500, someone told that, oh, time is not relative, if your moving time is different. It is complicated. I mean, even today, I mean, for that matter, special relativity, the moment you bring in that idea that time depends on position, it's not straightforward. But then we have so many experiments these days that you're ready to accept that. You don't like it, or you're not comfortable at all. It is intuitive, not at all intuitive, but you're ready to accept it because, okay, we see experiments in the atomic scale. This is what it is. Like, we don't see it so often, but in atomic scale it is, so we accept it. But in those days, there was no reason to accept. That's why you do that. And probably, like this is just an analogy, probably similarly, future affecting present is just too complicated that we don't even want to entertain the idea because we cannot do anything meaningful at that time unless we can check something. But having said that, there are good enough reasons that causality has to be true. Like causal, like everything that we see is something you do something and then the effect happens. So good enough reasons.
So
yes.
I remember at some point reading something called like retro causal quantum effect or something, where I wouldn't do it justice trying to explain it, but
yeah. So okay, now all the fundamental physics that is are at a very standard level respects causality. We don't know any event that does not respect causality, but there are proposals, there are good enough reasons to have quantities that are not causal. For example, a very popular one these days is if you're in quantum information, you have entanglement. Right? Yeah, what happens is that, and this is a kind of a nice idea, that you have two states that are entangled. That means, let's say, pretty much like angular momentum, if this is in a total angular momentum is 0. If we are in one state, then this one has to be -1, right? Because total angular momentum is 0. Now that is good enough. If you're in classical, you say that, oh, I measure the angular momentum of this. I know the angular momentum of the other one because I know that the total is 0, right? So you know information of the second side based on the measurement on the right side. That's great. But now the point is in quantum mechanics, it's a very statistical system, but if you don't go by the statistical word there, if you say this is just one system, this doesn't decide to be in the up or down state unless you measure it. Correct? So you make a measurement and then you make a second measurement, then it is already in the one state. If you make a measurement and statistically that was equally possible that it could have been in -1. But based on that choice, how does this know what to do? Right? So that information has to pass from this end to the other end. And the idea is that this happens instantaneously from what I gather in quantum information. And that could, so that's issue that will surely have issues with causality, but this is still going on. So maybe you should bring this up in your Actually, Dr. Bird is a good enough. He should be able to at least address these questions. Yeah. So, other than that, so maybe in that context, people do talk about what you're pointing out, Jordan. But I would say consensus, right, in these matters, is there is no right and wrong, but most of the time, any established theory, we have not seen non-causal effects yet. That's the way I would put it. Is that reasonable? Does that help, Jordan? No.
You give us a thumbs up.
Oh, you give thumbs up. Yeah, you should. I'm a little far from here, and I've pinned my video.
Oh, yes. Sorry.
You should put it on the. This is better. Yeah, at least we can see. Okay, so that's absoluteness there, and so T prime equal to T, but that's not what we wanted to discuss, right? That's Galilean relativity, and we are being more open. Let's see if there is any other room there, and we are saying that this is a function of B now, right? Okay, so. Oh, yeah, and our condition is that these two should be satisfied. So we put this, substitute this in there, and see for consistency, can we learn something out of it or not? That's our idea. And okay. So we substitute this in here. So we have A times Z plus B times CT square. That's Z prime square actually. Even here, yeah, plus X square. So this is, do this in 2 steps. So X prime square plus Y prime square plus Z prime square minus CT prime square is equal to 0. So since X prime is equal to X, that's X square plus Y square plus A times Z plus B times CT square minus of CDE times Z plus F times CT square is equal to 0. That should be true based on whatever we have proposed, that there is a linear transformation between them. So this is saying X square plus Y square plus collect the terms. There's a Z square here, there's another Z square here. So this is A square minus E square times Z square. And there is also a CT square here, CT square here. I want to write it as a minus CT square. So this is minus of F square minus B square times CT the whole square. And there are some cross terms there. Right? So it is plus 2 times Z times CT times AB minus EF is all equal to 0. Good. If this has to be true, we have to compare this with X square plus Y square plus Z square, but we also know that X square plus Y square plus Z square minus CT square has to be equal to 0. So we conclude that A square minus E square is equal to 1. That's one condition we can get. F square minus B square, these are all functions of velocity, remember, is equal to 1. And we also need AB minus EF is equal to 0, which means this has to be equal. There are 4 unknowns there. There are 3 equations here. It's very clear that we won't be able to find everything, right? But at least we learn something. So that's why I said we'll reach close, but we won't be able to derive completely. Somewhere we will have to introduce the physics. Okay, so that's good enough. So let's see what can we do here. So this 3 equations, let's see. Let's substitute E from here. So there's a square minus, so this leads to, if I use this 3rd equation, I can say this is AB over F square is equal to 1. And what else? And up here, so this is a square times F square minus B square over F square is equal to 1. Just implication there. But F square minus B square is equal to 1. So this implies that A square is equal to F square. Correct. Same thing, you can start from the 2nd equation, right? If A square is equal to F square, this also means that B square is equal to E square, right? If I square this, this implies that B square is equal to E square. Right. Of course, there are plus or minus conditions here, but as I said, we won't be able to solve this uniquely. We are going to use some property in there. So let's pick, right? Let's pick A equal to F. Right? This is not an implication. Let's pick A equal to F and B equal to E. Okay, let's pick that because we want one solution in there, and that's it. So we cannot go beyond that. So if I were to write all this with this information, if I can write these conditions again, what do I gain? A square. So we know that A square minus E square is 1. That's one relation. But if this is true, and if I assume this, that second one is implied by this. That's identical. And the third one is also identical because A over F is B over E. So this is also identical. So this is the only relation we need. Right? That's what we have there. And then we have the transformation. And again, one is known in the other, right? So there's only one unknown in this. Right? And it is connected through. So that's where you stand, at least based on the simple requirement that it's a linear transformation and that your light propagates identically. Oh, did I show the? And light propagates identically for both the observers, you immediately conclude this. And this should remind you of something in trigonometry, right? So cosine square theta plus sine square theta is equal to 1, but this is minus hyperbolic, right? So you think of hyperbolic functions. So you propose that let A be very good. So let's propose that some theta, like remember A was a function of velocity. So theta is a function of velocity here, right? Some angle theta, cosine hyperbolic of function, and let's say E is equal to sine hyperbolic theta. Right. That's again a proposition. So lots of jumps we have made, right? So, but that's where the other derivation is better. It comes out a lot more unique in that sense. But here, so let's do this, and then immediately you have what you say. What we are suggesting is that we have one parameter theta. So we have saying that as z prime is equal to cosine hyperbolic theta, whatever that cosine hyperbolic theta is, times z plus sine hyperbolic theta times ct, and ct prime is equal to sine hyperbolic theta times z plus cosine hyperbolic theta times ct prime. That's the proposition. And again, we haven't done anything except the fact that we still have one unknown, right? I said that there will be one unknown left, and that's this function theta, if you want. At this point, you say that, okay, I have to depend on physics to get this in a proper way. And this is that relativistic Lorentz transformation. Like, remember that Einstein, how he concluded is that he was trying to understand how electric and magnetic field transform between each other, which we will sort of derive after 2 weeks or so, how electric field looks like to a moving observer. So he's pretty much started from there, and these transformations were helping him see what is going on. But there was a lot of insight that went into this instead of this simple algebra. This is kind of retrospectively walking back and seeing that, oh, this is simple. But it was not. At least personally, I think it was not simple. Okay, so the physics connection comes by proposing that tangent hyperbolic theta, right, just remember theta is a function of v, is a simple relation. We say this velocity v, right, it cannot be v itself because it has to be dimensional, right? Tangent hyperbolic, so we say v over c. Okay. That's your physics connection. So this is physics telling, or trying to put it together, at least in this derivation. That's good, but and typically we say this is beta, right? That's it has become very standard to call this beta, at least in all the modern recent textbooks. It's we use the letter beta there. Okay, so but the transformation itself is in terms of sine hyperbolic and cosine hyperbolic. So what is sine hyperbolic or cosine hyperbolic theta in terms of tangent hyperbolic, right? What is it in terms of beta? Because that's more physical, right? So cosine hyperbolic theta. What's the relation between cosine hyperbolic theta and tangent hyperbolic theta? Because then I can write it in terms of v over c. Right, so go back and write this into secant hyperbolic theta. That's surely correct. And remember, like tangent, you have 1 plus tangent square is equal to secant square theta. So in hyperbolic terms, you have 1 minus tangent hyperbolic square theta is equal to secant hyperbolic square theta. So because 1 minus sine hyperbolic over cosine hyperbolic square minus sine hyperbolic is 1. So I can see that almost. And that is 1 over 1 minus tangent hyperbolic square theta. That's square root of that. And that's 1 over 1 minus beta square. And what is that commonly called in modern literature? Probably you guys have seen it here and there. This you say, we will say it to be gamma, right? That's gamma. Okay, it is almost out, right? But I'm getting better. So that's gamma. Okay. So cosine hyperbolic theta is going to be gamma, which is 1 minus 1 over 1 minus beta square, and sine hyperbolic theta then. Sine hyperbolic theta. Would squeeze this in there. So sine hyperbolic theta is equal to, now that I know cosine hyperbolic theta, I'll write tangent hyperbolic theta times cosine hyperbolic theta. Right? That's surely right. But tangent hyperbolic theta is beta, and cosine hyperbolic theta is gamma. Right? So it's beta gamma. So we have our relation, if you want, to be our Lorentz transformation is Z prime is equal to gamma times Z plus beta gamma, right, times C times T, and C times T prime is equal to beta gamma times Z plus gamma times C times T. Correct. Okay, so that probably in a very, not a very elegant proof, but the nice part at least is that from the fact that light looks the same for two observers, at least this is consistent with that. Right? That's the way to, that's the best we can say in this way of looking at it. But now let's see what's the conclusion, what's the implication of this, right? That's more useful. So let's say, let's write this down as Z prime CT prime, since some, I think we are comfortable with matrices, it's the same information, but let's write this in this form. Beta gamma. In fact, gamma can come out, right? So that's Z times CT. So that's a way of looking at it. One should compare this with, so let's say, so this is called Lorentz transformations. It involves time, but one can also think of, remember, this is, I'm writing x prime y prime, which is perfectly fine, but there is no time here now, notice, right? This should be compared with, suppose, cosine theta, sine theta, sine theta, cosine theta, times x and y. What is that represent? Probably nothing.
Rotation.
Rotation, right? Yeah, that's correct, but I made a mistake. That should be minus. Right, that should be a minus sign that I intended to think of it as rotation. So, and what is so cool about rotations? What stays the same when you rotate your coordinate system? What quantity stays the same? Think of something that's, you don't have to do anything, it's identical when after you rotate it. Magnitude or the length. Yes. Jordan, you were saying something? Say same thing?
Oh, I just said distance.
Yeah, distance, right? And how do you see that? You would say, oh, x prime square plus y prime square is equal to cosine theta x plus sine theta y. X square. Am I still on the board? Oh, it's lots of plus minus sine theta x plus cosine theta y square. And you would say, oh, cosine square plus sine square theta x square plus sine square theta plus cosine square theta y square. And that is a cancellation plus 2 cosine theta sine theta xy minus 2 cosine theta sine theta xy. The cancellation is important. And then we use trigonometry to say, ah, that's x squared plus y squared. That's an invariant quantity, which in rotations we, since we learned it quite early, we say, oh, that's nice. Distances remain the same. Here, what is going on? There is a very similarity in this way of looking at it. And notice, first of all, we can, let's first think of it as z prime. Now this is time, notice. This was two positions, this is time. This was a rotation transformation, this is a very different transformation. First, let's look at this, because gamma we said was cosine hyperbolic theta, right? That's sine hyperbolic theta, that's cosine hyperbolic theta, and that's x times y. Oops, z times ct. This is a Lorentz transformation. This is not rotation. It looks maybe has a similarity, but very different, right? That's a minus sign there. First of all, it's hyperbolic, right? But it's a 2 by 2 matrix. And again, let's see what happens like that, right? Like, is there any invariant quantity here? Invariant means something remains the same. So taking the motivation from there, let's do the same thing. C prime square this time minus c prime square. Right. And why minus? Because we know that cosine hyperbolic square minus sine hyperbolic square is equal to 1 this time, right? So this turns out it's cosine hyperbolic theta times z plus sine hyperbolic theta times c times t square plus sine hyperbolic theta times c plus cosine hyperbolic theta times c times t square. And again, oh, that's it, right? So that's equal to, some mistake, because this is minus, right? Minus. So cosine hyperbolic square theta minus sine hyperbolic square theta times z square plus sine hyperbolic square theta minus cosine hyperbolic square theta times c t square and plus 2z ct cosine hyperbolic theta sine hyperbolic theta minus 2 z ct sine hyperbolic theta cosine hyperbolic. Of course, this cancels out. That's equal to 1. And this is equal to minus 1. That's minus c squared. T squared. Should be straightforward. Any questions as of now? Any comments or questions? There's similarity between Lorentz and this. So this is this will become a very important quantity very soon, right? There's this minus sign and a distance, right, between them. And so if you want, if you're doing geometry of rotations is described by rotations, correct? Sorry, geometry of rotations is described by circle, right? X square plus y square is equal to a constant, right? That stays the same. What is a curve which has z square minus c square t square is equal to constant? What curve is that? So x square plus y square is equal to a constant. That's a circle, right? So a circle, if I were to transform it, I can rotate my frame, will look like a circle, right? In any frame that you're in. But now let's say there's a z and a t. Let me put z on the x-axis and c times t. And now I'm looking for something like z square minus c square t square is equal to constant. What's that curve?
A hyperbola?
Hyperbola, right? And an ellipse is x square. What? I'm confused now. What is it? Ellipse? Hyperbola?
Like x squared over a squared.
Yes, exactly. Yeah, so
A squared.
good. Yeah, that's what I was like. So x square plus y square over b square is equal to 1. That's an ellipse, make this minus, and that's a hyperbola, right? And that's a special case now, in the sense A is equal to B, right? And hyperbola looks like, how does it look like? If you were to have two 45-degree lines, right? This will look like, this will be asymptote to these lines. This will be like this. Okay. Or it can also be this. Or it can also be this, like the plus or minus quantities. So it depends on which constant is this. Like if this constant is certain kind, then it is in particular quadrants. Okay. So hyperbola, first of all, has a very close connection with the circle in the sense that, like as circle plays a role in rotations, hyperbola plays a role in Lorentz transformation. There is a nice problem you can talk about in this. If you, I don't know whether I mentioned it to you guys. So this is a problem I think posed by UREC. This is Dr. Kochik in the math department. Pointing about that, if you guys are interested in talks related to math and relatively simple, how do you say, simple things in life maybe, he organizes a talk every Thursday at 2 o'clock, and this semester it was not going on for a few weeks, so the first one meets today at 2 o'clock. So feel free to join if you're interested. Ask Moses. I see that he often attends. So
yeah, I was planning to attend today. I might even ask him about this since.
Yeah, exactly.
Yeah.
Yeah. So he's sort of he enjoys this thing, the connection between circles and hyperbola. That's his. And your homework has a connection with his work. So the Poincare addition or the relativistic velocity addition. We know most probably you have all seen it. He gave a very simple geometric picture of doing this using circles. And in fact, he has a small app which you can move around. And that I give the link of that in your homework. I'll encourage. In fact, that homework, that particular problem, you can use the app. You don't have to do the algebra. So the whole idea is that no algebra. And it is good, especially when you are thinking about. You can ask what happens if you hypothetically say that there are two particles moving faster than speed of light. And if you think of velocity addition in that context, our intuition fails. But then if you trust the algebra there of the Poincare addition, you can get some conclusions there, which is kind of, anyway. So his point is the following. I think these are called Platonic solids. And Platonic solids works for a sphere, right? But let's say, and what are Platonic solids, by the way? Anyone?
Regular polygons that have all of their faces are the same shape.
That's exactly correct. Tell it again, Michael. It was very well said. Regular polygon, yeah.
Yeah, regular polygons that all of their faces have the same shape.
All the faces have the same. But this is 3-dimensional. I can tell it much more easily in 2 dimensions. So in 2 dimensions, you talk about polygon will be, so this will be a triangle of the same length. Like, so you take a circle and put 3 dots, and they should be all equidistant. Right? That's an example. This is also an example. Square, it should be all equidistant. Next one is pentagon. Right? And so in 2 dimensions, there are lots of Platonic solids. Platonic, in this case, won't be solid, right? Platonic elements, let us say. But in 3 dimensions, remarkably, there are only 5 of them. Like only 5 of them you can consider. One is a tetrahedron, one is a square, or sorry, cube. Third is an octagon, and few more, or quiz, find that out. Okay, find the list the 5 Platonic solids. Just and kind of define the Platonic solids as Michael very nicely defined. Now the question is, okay, so this is all for circles, right? And you ask, okay, so for in Lorentz transformation, a circle is replaced by a hyperbola, only one hyperbola, right? So all these, so take any 2 points, right? And the distance is decided by this, z square minus c square t square. And now again ask the same thing, that can you define Platonic solids in a on a hyperbola? Or how many Platonic solids exist? So how many, so you start from here, and you have to remember, what does it mean to be the same, right? Like length being same doesn't mean it is not normal measurement now, right? It is z square minus c square t square. So the length differences might be very non-trivial in this. But get that intuition, and you ask how many are there. And yeah, so that's an for solutions or more insight, ask Dr. Kochik. Today you can ask if you want. Yeah. Okay. So that's a small digression, right? Let's leave this aside for a moment. Let's come to algebra, right? That was geometry for some time. So let's do algebra, and instead of cosine hyperbolic theta, we have gamma, right? So let's see how this works with gamma, right? This was very convenient because we use the hyperbolic definitions. So let's see how this works with gammas and betas.
Before we proceed, can I ask a question?
Yes, you should.
So, yeah, I don't know if I'm being too picky, because I agree with all of your algebra, but it seems to me that this transformation matrix, the hyperbolic one, has determinant 1.
Determinant, yeah,
right?
what's wrong with that?
So that would mean that it's in like that it's a special orthogonal matrix. So
it's not orthogonal.
it's not. Oh, wait.
It's not orthogonal, right?
Wait, but those are real. Like each element is real.
Yeah, but orthogonal will require this times this plus this times this, right? Remember, the scalar product is tricky here, right?
Yeah, so that's what I'm confused about, because like orthogonal matrices are real valued matrices with determinant 1 or -1, correct?
Yes, but
So-
this is
Yeah.
this
so I
is
don't
not an
understand how this
orthogonal
is
matrix.
Orthogonal.
And first of
But-
all,
but
there
why?
is this very why? I mean, there's a bigger issue here, right? If you really want to go along that direction, is that this will be called the distance, right? If you're doing rotation, you have x square plus y square is equal to a constant, which you will interpret as the distance between 2 points, let's say from one of them as origin, right? And distance usually is positive, right? You don't talk about negative distances, especially the square of them, right? And here we can have negative. Like negative distance or negative metric is not positive definite, if you want, right? And we will talk about that in the sense that it will lead to what is called space-like, time-like. It will play an important role, that indefiniteness, but it is to begin with, it is not a normal space. Like you call it in mathematics a manifold, right? A manifold has to do with how you define a distance on the manifold. Here, the distance is pretty non-trivial. It can be negative, as simple as that. What does it mean by negative distances? But we're talking about time. So we will give some interpretations to this, or we will give concrete interpretations to what it means to have negative distances. Right? It will mean time-like quantities. So so how do I answer your question? Yeah, so you said you're picky, so be picky, yeah.
Yeah, so because my understanding is that if the values of the matrix, if the elements are real and the determinant is 1, it would be a special orthogonal matrix. So it would preserve the normal Euclidean distance.
Okay,
So,
that assumes a scalar product. That definition assumes a scalar product in the sense. So what you're saying is that give me so you say 2 vectors and A dot B. So there is a way you say this, right? This is equal to AX or A1, B1 plus A2, B2, right? This is a rule you provide. This is called a scalar product. If you provide this rule and then you write a matrix, right? And let's say this is A11, A22, A21, sorry, A12, and A22. And now you say that, okay, if A11 times A12 plus, so think of this as a vector, this as another vector, and then take the dot product, then you say that, oh, this is orthogonal, right? But you require a scalar product to begin with. This is a different scalar product altogether. There is a minus sign in between, right? So it's a different entity there. In that sense, it is orthogonal. So in the new scalar product, it is orthogonal, right? But you don't say it is, what do you call it? It is called SL. S stands for the determinant 1. It is S. It's not orthogonal, put it like that. It's not an orthogonal. Yeah. Okay. Yeah, it's called SL. L stands for, I don't know what. Yeah, linear. Yeah. Go ahead.
So this column, inner product column, is the more fundamental definition, and that implies the determinant 1 condition for Euclidean space. Is that true?
Repeat that.
So the more fundamental definition is this, what you have drawn, like the column dotted with the column.
Yeah, but then to dot that, I need a rule, I'm saying.
Okay, yes.
If you give me the rule, so for example, in general, there will be a Gij. Okay, I'm going to use some jargon here. A dotted with B. So now in general, my scalar product could be AI Gij times Bj, where Gij is some constants. It could be any matrix. In this case, it is 1, 0, 0, 1. Right? It could be given any matrix that sets my rule, and that sets my transformation, and then I can go and talk about orthogonality then. Correct? And, and rotation is in, so SO2, right? So this is rotation in 2 dimensions. Okay. What that means is that this is diagonal, this quantity is diagonal, and this is 2 dimensions, and S stands for what you're saying is determinant 1, and O stands for orthogonal. Now, this quantity here, the Lorentz transformation, is orthogonal, but this is called 1, 1. So this is Lorentz transformation in 2 dimensions. In 2 dimensions, 1 plus 1 dimension, 1 space and 1 time. And what that means is that the one of the quantities in the metric is plus and the other one is minus. The one plus sign and the other one is minus sign. Does that help roughly?
Yes.
So the most general Lorentz transformation will be SO31. 3 dimensions and 1 time dimensions. And rotations is SO3. Right? So put that all together. And SO3 is related to SU2, SO31 is related to SL2C. So lots of group theory in there, but let me not go in there. I mean, it's
Okay,
nice, things, very nice, but I think let's not go there now.
Yeah.
Talk to
Thank
me
you for
later.
taking that time.
Yeah,
Yep,
yeah,
I will.
yeah. Okay. So, yeah, I was saying that, yeah, can we see the same thing with gammas, right? Some properties. So there must be some relation between gammas which allow you to put this one, right? It must be possible to do that indirectly with that. So let's see that. It's in the last 5 minutes, we can do that and then do the implications of this. Remember, what are the implications, Lorentz? What is it? Length contracts, time dilates, and velocity addition, simultaneity. What else? Yeah, we'll talk about that. First, let me do this. Okay. Now we have the same thing should happen. Let's quickly do this. Gamma, beta, gamma, beta, gamma, gamma, my gamma. C, T. So let's again try to do z prime square minus ct prime square is equal to gamma times z plus beta gamma times ct square minus of beta gamma z plus gamma c times t square. This has to be, in fact, we already showed that this has to be equal to z square minus c square d square. So we kind of see what's going to happen. So let's connect this together. So it's gamma square minus beta square gamma square times z square. And then minus, again do the same thing. So it's gamma square minus beta square gamma square times c t square, and there is the cross term, right? Plus 2z ct beta gamma square, and this is minus 2z ct beta gamma square. This surely cancels out, and this seems to suggest that gamma square minus beta square minus beta square gamma square should be equal to 1, right? Which we can check. This is equal to 1 minus beta square. Let's check that. 1 minus beta square times gamma square. That's almost obvious, I suppose. Am I still on the board? No. Oh, almost. So 1 minus beta square 1 over 1 minus beta square, that's equal to 1, right? So this is, you will see this, just keep this property in mind. There are some more properties we will see, which is very useful. Since I have 2 more minutes, I can at least tell what other things we will do. Next time we want to, actually, homework should be postponed right now because I didn't finish. So feel free to have the homework postponed because the next homework is actually not due at all. So I'll postpone it to at least Thursday. So what we wanted, implications of Lorentz transformation is that length contracts. What does length contract mean? From your earlier physics?
As you approach the speed of light, it almost looks like the object rotates in another dimension and shortens.
Yeah, shortens. Like we will all. Have you guys seen this videos on this? It's remarkable that there is not many videos made to show Lorentz transformation, but there is one of them. I think it was about 5-10 years back, made by MIT group. It's called slower than light or something. It's a
There-
game.
there's a nice video. There's a nice video that talks about if you have a 12-foot ladder and you want to fit it in an 8-foot barn, how do you do it?
Yeah, those are puzzles. Those are paradoxes. But I'm saying with all the video gaming softwares available, one should actually go and you see the world around you. How will the world look like if you were going at 2 times or half the speed of light? Right? They should show that. And this was attempted by an MIT lab. I think it is called slower than light. Something like that. It was not that jazzy, but it did, at least the physics was shown correctly. It didn't come out very attractive or dramatic in the sense, but I think it's called slower than light. So length contracts, second is time dilates. What is the consequence of time dilates? You travel and you get younger, or relatively speaking, you get if you travel a lot, you don't get old very fast. Third is velocity addition, non-trivial velocity addition, or light does not add up at all. And then the most best one is simultaneity. There is nothing called simultaneity in relativity. Like if two things happen at the simultaneity has to do with two things happening at the same time, right? It's like saying here I drop this pen and the cap of the pen. Yeah, so I drop this two identically. So that will be identical, right? I let them go at the same time. But for someone moving, this is not the same. One can make this go this way, that way. This can be before that, this can be before that. So, but that's not violating causality, by the way. So you have to put your head around that. And that's, I think, the most non-trivial one. And what? And you can have an object right next to you, but you may not be able to see it. Okay, we talked about this example. You could be right adjacent to another object, but you might never see it just because of the dynamics of the two objects. And if one is approaching the other and leaving in two different cones, we will, or at least I'll show a simple example where you don't see the presence of the other. It's like saying there could be another universe right next to you, but you will never see it because of the kind of motion that happens. So those are the non-trivial things that come in very cool. But okay, I'll stop here and enjoy.
So I have one quick question that was regarding what Luke had brought up. That I got a little more confused by when you showed the matrix for the Lorentz transformation. Because if you take the inverse of that, you end up with the identity matrix, which means that it's orthogonal. So now I'm really confused. And
Tell me again, what's the confusion? So let's say you want to write hyperbolic or gamma?
just use the gammas, I guess, for
Gamma. So gamma, beta gamma. Yeah.
and then
The inverse of this,
multiply this by its inverse, gamma times minus beta gamma minus beta gamma
Yeah.
and gamma, and you'll end up with the identity matrix,
That's correct.
which means it's orthogonal.
Yeah, so maybe I should say it the following way. Okay. Remember that I said SO31, right? Or SO11, right? It stands for orthogonal. So this is an orthogonal matrix. Let me put it that way, okay? But it is not orthogonal in the traditional sense that orthogonality needs a scalar product. It needs this 1,1 scalar product. So what I mean is that, for example, if you, so what is orthogonality? A, B, C, D. If this matrix is orthogonal, one of the requirements is that A times B. In the standard scalar product, it will be C times D has to be equal to 0. Like orthogonal means the vector constructed out of this, dotted with this, so that's AB plus CD is equal to 0. Right? Are you with me? But now this matrix is orthogonal, but now in a different dot product is AB minus CD that is equal to 0. So scalar product is different now. So it is orthogonal, but my definition of orthogonality is different now.
Oh, okay. Okay.
Right,
I
so
see what you're saying. Yeah.
it's like
I guess
saying-
I've never even done that before.
Yeah, so it's a nice thing in rotations. This is perpendicular, right? This is X and that's Y. That's perpendicular, right? In Lorentz transformation, that's not what perpendicular means. So this is C and T. These two are perpendicular. These two are perpendicular. Geometry is different. Talk to Urek, he will love talking about that. He can visualize these things much. I mean, he has a lot. I mean, he works. His work is there. So I can only do simple geometries in that, but he can probably construct a castle in that space. So, okay.
Okay, thank you. That answered my question.
Okay. Good.
Does everybody have the link, by the way? To
Yeah,
the,
can you forward that?
Yeah, I can forward it.
And I should stop now if I have to reach there on time. That gives you a motivation. That will be a motivation for me to stop. Yeah. Okay. Enjoy, guys.
Okay, bye-bye.
Thank you so much.
Bye, Jordan. Yeah. Bye, Luke. Yeah. Bye, Alia. We don't get to see Alia these days. Yeah.